Hello! In this module we're going to learn about a number of different useful derived rules. We've already learned one version of De Morgan's, and I'm going to talk about some others in this video, and then in other videos in this module I will show you how to derive some of those other useful rules and give examples of how they can be used in derivations to make our derivations easier. In this video I'm just going to list some of them and talk generally about how they would be useful, and then we'll see how they would be useful, actually applications of them in some other videos. We're going to start with some rules that describe how negation distributes over other operators. In mathematics, we can see that negation interacts differently with different operators. So let's say we have minus 5 plus 7. Well, that's the same. So 5 plus 7 is 12. Negative of that is negative 12. We can move that negative or minus sign inside and put it on both the 5 and the 7. We have minus 5 plus minus 7, and that comes out to minus 12. So in that case, when we move the minus inside, it goes on to both of them. But what about minus and multiplication? Well, so minus of 5 plus 7, or times 7, 5 times 7 is 35. The minus of that, minus 35. If we move the minus sign inside, then it goes on just one of them. We have minus 5 times 7, and that's also minus 35. So in the one case, when you move the minus inside, it goes on both of them. In the other case, it goes on just one of them, and they stay the same. The plus and the multiplication signs stay the same. So what we can see is that in mathematics, minus distributes differently over different operators, and it's the same thing in logic, except it's a little bit more complicated. So let's say here's a list of how negation distributes over each of the 4 different other operators. So if you have negation negation of P arrow Q, that says the conditional is false. And when is the conditional false? In only one situation, when the antecedent is true, so P is true, and Q is false. So P and not Q, those are equivalent. Negation of P, if P then Q, that's equivalent to P and not Q. The negation of a disjunction, that's one of the De Morgan's rules, and that's the one we've already learned that we talked about in class. So that's negation of P or Q, that's equivalent to not P and not Q. If the disjunction is false, that means both the pieces are false, so the negations of both the pieces are true, conjoin them, or adjoin them, and you have the conjunction, and vice versa. The negation of a conjunction, negation of P and Q, that requires that the conjunction be false, and that requires that one of its 2 pieces be false. So it requires that either P be false or that Q be false, which is what not P or not Q says. Negation of P if and only if Q. Well, P if and only if Q, that's true when P and Q have the same truth values. So the negation of P if and only if Q, that's true when they have different truth values. Well, another way of saying that is to say that not P is true if and only if Q is true. P is false if and only if Q. And so we just move the negation inside and put it on one of the 2 pieces of the biconditional. So those are the 4 ways in which the negation distributes over the different operators besides the negation. And we can have biconditionals that state all of those, and these are all theorems, and they're all tautologies. So these are the biconditional sentences in the language that state the 2 pieces are equivalent, and in fact they are, and these are all logical truths. They're true on every row of the truth table, and they're theorems. They can be derived from no sentences, using no premises. So these give us a bunch of derived rules. We have all the De Morgan's rules, which we have on the top there. If you have the negation of a disjunction, you can turn that into a conjunction of negations and vice versa. A different version of De Morgan's says if you have the negation of a conjunction, you can turn that into a disjunction of negations or vice versa. And then on the bottom, we have NC for negation of a conditional. If the conditional is false, then P and not Q is true and vice versa. And then the rule for the biconditional that we just, if the biconditional is false, then you can just move the negation inside and put it on the first piece of the biconditional. And these are all listed in this good derived rules table, and these 4 are right at the top because they're super useful, and we have their problem numbers listed over here as well. So that should actually be 240. So these are super useful rules. We've already done this one together. This one has been homework. I'm going to show how to do it in another video. I'm going to show how to do this one in another video in this module, and we'll talk about this one later. This one is pretty long. So those are a bunch of really useful rules. The most useful rules are the top of each one, because what they let us do is they mean, oh, now I can do, when I have the negation of something complex, now I can do something with that. Previously, if you had the negation of something complex, you had to do show unneg, and so you had to do a big subderivation. Now that we have, once you derive these rules, you don't have to do the show unneg subderivation anymore, because now you can do something else with that line, the negation of something complex. You can turn it into something that's not a negation, right? You can turn the negation of the disjunction into a conjunction, which you can use. You can turn the negation of the conditional into a conjunction, which you can use. You can turn the negation of a biconditional into a biconditional, which you can use. You can turn the negation of a conjunction into a disjunction, which you can use. So each of these rules says you have the negation of something complex, not very useful. Let's turn it into something else that we can then use, that we have rules that do apply to. So these are really useful because they let us skip the show unnegation subderivation. So very useful. There are several rules that I want to talk about now that have to do with the conditional. And we call our conditional, our arrow sign, the material conditional for reasons that I'm not going to talk about, but we want to remember that it's a little funny how it works. So if we remember, the only way that the conditional can be false is if there's a counterexample, if the premise is true and the conclusion is false. Otherwise, if both pieces are true, or if the first piece is true and the second, if the antecedent is false and the consequent is true, or if the antecedent and consequent are both false, then the conditional is true. So it's very hard for a conditional to be false. The only way it's false is if the antecedent is true and the consequent is false, and otherwise the conditional is true. So if we think about what that means that this, if Q, then if P, then Q, that's a tautology and it's a theorem. Why? Well, let's look at the truth table. There are two rows on which the antecedent is true, the first row and the third row. And on both of those rows, the conditional is also true. So if Q is true, then you're on the first or the third row, and either way, the conditional is true. And it's the same thing with this other theorem. This says that P is false. Okay, so that says the antecedent is false, right? Well, what does that mean? It means you're in one of these two rows, because these are the two rows, the bottom two rows, on which the antecedent is false, and lo and behold, the conditional is true on both of those rows. So both of these are tautologies, and they're theorems. We can prove them without any premises. This basically says that, more or less says that. It says the conditional is equivalent to a disjunction, right? The conditional, there are two ways for it to be true. Either the antecedent is false or the consequent is true, right? If either of these are true, then the conditional is true, and if the conditional is true, they're on one of these three rows, and on all of these three rows, either the antecedent is false or the consequent is true. And so we can get, if we derive the theorems for these, and again, these are listed in this table, we've got, actually, let's look at the rules first. So we have two rules that say if you have the negation of the antecedent, you can write down the whole conditional, and if you have the consequent, you can write down the whole conditional. These are both called MC for material conditional. And then these two rules say if you have a conditional, you can turn it into a disjunction, and if you have the right kind of disjunction, one where one of the disjuncts is a negation, then you can turn that into a conditional. And that's called CDJ for conditional disjunction. And these are particularly useful because they let us build conditionals. For disjunctions and conjunctions and biconditionals, we have rules that let us build them. We have ADJ for conditionals, we have ADD for disjunctions, and we have CB for biconditionals. Well, these two rules, derived rules, MC, now we can use to build conditionals. And so they're handy. If we look on the table, we see, okay, there's MC1, the two versions of MC, their theorems, there are problems 1.102 and 1.18, and then the CDJ rules are down there at the bottom. Oh, these are actually different versions of CDJ, but there are two versions here, and the one that I'm showing you in the keynote is this CDJ 2.4. So you can derive all of those.
And actually one of these is a variation of CDJs for homework. You want to use De Morgan's. And then lastly, we have the rules called biconditional ponens and biconditional tolons. And these help us use biconditionals. So BP has two forms. So if you have a biconditional and you know that one side is true, then you know the other side is true. And same thing, if you have a biconditional and you know the second piece is true, then you know the first piece is true. Those are BP. And then if you have a biconditional and you know the first piece is false, you know the second piece is false. And if you have a biconditional and you know that the second piece is false, then you know that the first piece is false. And these are extremely easy theorems to prove. The theorems associated with these, again, listed in this handout. They're BP 1 and 2 and BT 1 and 2, so 274 through 277. Very straightforward derivations of some very simple theorems. And these are helpful because they just help us use biconditionals more quickly. They make the derivation less cluttered because we don't have to break the biconditional up into conditionals. So those are a bunch of derived rules. And in the rest of this module, I'm going to do some videos that are going to show how to derive some of them. Others you have for homework, the easier ones. And then I'm also going to have some videos showing how we can actually use these these rules to make our lives easier in a variety of derivations. So let's go and look at some of those derivations.